Welcome to this Class 10 Physics lecture on light, reflection, and refraction. Light is a form of electromagnetic radiation that can be detected by the human eye. It exhibits dual wave-particle properties and travels in straight lines under ordinary circumstances, a behavior known as rectilinear propagation. When light strikes a surface, it can undergo reflection, refraction, or absorption. In this lecture, we will study the laws governing the reflection of light by spherical mirrors, explore the mechanics of refraction through glass slabs, trace image formation through spherical lenses, analyze the human eye optical system, and observe how a prism disperses white light into a spectrum of colors. Reflection occurs when light rays bounce back into the same medium upon striking a polished boundary. The laws of reflection state that the angle of incidence is always equal to the angle of reflection, and the incident ray, reflected ray, and normal all lie in the same plane. Curved or spherical mirrors have reflective surfaces that are parts of a hollow glass sphere. In a concave mirror, the reflecting surface is curved inwards towards the center, which acts as a converging mirror. In a convex mirror, the reflecting surface is curved outwards, which acts as a diverging mirror. Key terms include the center of curvature C, the pole P, the principal axis, and the principal focus F, where parallel rays converge or appear to diverge. To solve optical problems for spherical mirrors, we use sign conventions called the Cartesian sign convention. Here, the pole is treated as the origin, objects are placed to the left, distances along the incident light are positive, and height above the principal axis is positive. The mirror formula relates the object distance u, image distance v, and focal length f, which is expressed as 1 over v plus 1 over u equals 1 over f. The focal length is always half of the radius of curvature. Magnification m is the ratio of image height to object height, which is also equal to minus v over u. A negative magnification indicates a real and inverted image, whereas a positive magnification indicates a virtual and direct image. Refraction is the bending of light as it passes obliquely from one transparent medium to another of different optical density. This bending occurs because the speed of light changes across media. The laws of refraction state that the incident ray, refracted ray, and normal all lie in the same plane. Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media, written as sine I over sine r equals the relative refractive index. The absolute refractive index of a medium is the speed of light in vacuum divided by the speed of light in that medium. When light travels from a rarer to a denser medium, it bends towards the normal, and when moving from a denser to a rarer medium, it bends away. When light passes through a rectangular glass slab, it undergoes refraction twice, first at the air-glass interface, and then at the glass-air interface. At the first interface, the incident ray bends towards the normal because glass is optically denser than air. At the second interface, the refracted ray bends away from the normal as it exits into air. Because the opposite faces of the slab are parallel, the angle of emergence is equal to the angle of incidence. This causes the emergent ray to be parallel to the direction of the original incident ray, although it is shifted sideways. This perpendicular distance between the original incident path and the emergent path is called lateral displacement. A lens is a piece of transparent refracting medium bound by two surfaces, at least one of which is curved. A convex lens is thicker at the middle than at the edges, acting as a converging lens that bends parallel rays inwards towards a principal focus. A concave lens is thinner at the middle than at the edges, acting as a diverging lens that bends parallel rays outwards. Like mirrors, we define a lens formula relating object distance u, image distance v, and focal length f. 1 over v minus 1 over u equals 1 over f. The magnification of a lens is the ratio of image height to object height, which is also equal to positive v over u. The power of a lens is the reciprocal of its focal length in meters, measured in dioptres. The human eye is a natural optical instrument that uses a living double convex crystalline lens to focus light on a light-sensitive screen called the retina. Light enters the eye through a thin, transparent membrane called the cornea, passes through the aqueous humor and is regulated by the iris and pupil. The crystalline lens is held in place by ciliary muscles. These ciliary muscles can alter the curvature and focal length of the lens, a capability known as the power of accommodation. To see distant objects clearly, ciliary muscles relax, making the lens thin. To see nearby objects, ciliary muscles contract, making the lens thick and curved. The near point of a normal eye is 25 centimeters. Myopia, or nearsightedness, is a common vision defect where a person can see nearby objects clearly but cannot see distant objects distinctly. In a myopic eye, the parallel rays from a distant object are focused in front of the retina instead of exactly on it. This defect occurs due to either excessive curvature of the eye lens or elongation of the eyeball. The far point of a myopic eye is closer than infinity. To correct myopia, a concave lens of appropriate focal length and power is placed in front of the eye. The concave lens diverges the incoming parallel rays slightly, so that the eye lens can focus them exactly on the retina, restoring clear distance vision. Hypermetropia, or farsightedness, is a vision defect where a person can see distant objects clearly but cannot see nearby objects distinctly. The near point of the hypermetropic eye is shifted further than 25 centimeters, and light rays from a nearby object are focused behind the retina. This defect is caused by either the focal length of the eye lens being too long or the eyeball being too small. Hypermetropia is corrected using a convex lens of appropriate power, which converges incoming rays to help the eye focus them on the retina. Presbyopia is a defect of aging where the eye lens loses its flexibility and ciliary muscles weaken, making it difficult to focus on near objects, which is corrected using bifocal lenses. A glass prism is a transparent solid with 2 triangular bases and 3 rectangular lateral surfaces. Unlike a rectangular glass slab, the refracting faces of a prism are inclined at an angle, called the angle of the prism. When a ray of light enters the prism, it bends towards the normal at the first surface and bends away from the normal as it exits the second surface. Because the surfaces are not parallel, the emergent ray is bent at an angle relative to the direction of the original incident ray. This angle between the incident ray and the emergent ray is called the angle of deviation. The magnitude of this deviation depends on the prism angle and the angle of incidence. When a narrow beam of white light passes through a glass prism, it splits into a band of 7 distinct colors: violet, indigo, blue, green, yellow, orange, and red, a phenomenon called the dispersion of light. This band of colored components is called a spectrum. Dispersion occurs because different colors of light travel at the same speed in vacuum but at different speeds in glass. Therefore, they refract by different angles. Violet light deviates the most because it travels slowest in glass, while red light deviates the least. A rainbow is a natural spectrum appearing in the sky after rain, caused by the dispersion, refraction, and internal reflection of sunlight inside microscopic spherical water droplets acting as tiny prisms. Scattering of light is the deflection of light rays in random directions by microscopic particles like dust, water droplets, and gas molecules suspended in the atmosphere. The Tyndall effect is the scattering of light by colloidal particles, making the path of the beam visible. According to Rayleigh's scattering law, the intensity of scattered light is inversely proportional to the 4th power of its wavelength. Since blue light has a much shorter wavelength than red light, it is scattered much more strongly by gas molecules in the upper atmosphere, which is why the clear sky appears blue. At sunset and sunrise, light travels through a thicker layer of atmosphere, and most blue light is scattered away, leaving only red light to reach our eyes. In this comprehensive physics lecture, we have studied the nature of light through reflection and refraction. We analyzed reflection by concave and convex mirrors, calculating image details with the mirror formula. We explored refraction through glass slabs, detailing Snell's law and lateral displacement. We calculated optical power and focal lengths for converging and diverging lenses. We investigated the human eye, examining myopia and hypermetropia defects along with concave and convex corrective lens setups. Finally, We observed how prisms disperse white light into a rainbow spectrum and how atmospheric scattering causes the blue color of the sky. Mastering these optics laws is essential for physical sciences.